All right. Good afternoon, everyone. I don't know what time you're actually watching this video at, so good morning, good afternoon, good evening. It's good to be back looking at chapter 11.1, testing claims about a mean. So, as last chapter in chapter 10, we were doing confidence intervals for mean, a lot like chapter 8. Um, Chapter 11 will be like chapter 9 in significance testing, but instead of about a proportion, it will be about a mean. So, our learning targets state and check the random 10% normal condition for performing a significance test about a population mean. We should be good at that already, but we'll go over it again. Calculate the standardized test statistic for and p-value for a test about a population mean. So really only one small difference compared to chapter 9. Um, and then perform a significance test about a population mean and use confidence intervals to make a conclusion for a two-sided test about a population parameter. So I really like the last one, connecting in our chapter 10 to chapter 11 a little bit here. So 10% conditions, we should be pretty familiar with it. Oh, sorry, not to their 10% condition. Conditions for significance testing, we should be pretty familiar with it. There are three of them. Number one is the random. The data comes from a random sample from the population of interest. 10% when sampling, remember this is only about sampling, without replacement, n is less than 10% of the population size. And then normal/large counts. There's a couple ways you can satisfy this, and they should all be familiar to us from chapter 10. The first option is that the data comes from a normal distribution. Um, the second is the sample size is larger than 30. If neither of these are true, um, then you will take the sample size uh, and make a graph to decide if it's the normality of it, to see if it's relatively normal or not. So we're really looking for no strong skewness and no outliers. A test tip, just for all you guys out there, a graph in the calculator is not sufficient. You have to sketch the graph on your paper and make a statement saying this graph has no outliers or and no strong skewness. You must state that so that the grader knows that you know how to verify this condition. So let's look at an example. We have 15 deluxe AAA batteries from a company's simple random sample. Check the conditions for performing if significance tests are met. So random, an SRS of 15 random, 15 deluxe AAA batteries. And this is just something I want to remind us. I know sometimes the problem just says random, and we're quick to say SRS. We love simple random sample. If it doesn't say it's a simple random sample, if it just says a random sample of blah, 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 just say a random sample. Don't say an SRS or a simple random sample unless the problem specifically states that. Here, it does state that, right? So we're able to say that for our randomness. Our 10% condition, we're going to assume that 10% is less than 10% of all of the company's AAA batteries. Or you could say 15 is less than 150 of all batteries, or there's at least 150 batteries from this company. And looking at the dot plot, um, there's not really any skewness, a lot of, and there's no outliers. So we're good to continue on. So our conditions have been met. Now, after our conditions are met, we would jump into the do phase. And that's where we find our standardized test statistic. And that's from our statistic minus a parameter over standard deviation. And we've been looking at this for a while. So normally that's a z-score, what we've been talking about. In an ideal world where we know the mean and, well, we're assuming mean is equal to mu naught. But if we knew our population standard deviation, if we knew sigma, then we could go ahead and use a z-score. However, we almost never know the population standard deviation because we don't know the population mean. That's what we're trying to find in this case. So if we don't know the sigma, we will use the sample standard deviation, S sub x, and therefore we cannot use the z-score. We must use a t-score. All right, so the formula we will be using is t is equal to x bar minus mu naught divided by S sub x over square root of n. And then when we are performing these inferences about a population mean and using the t-distribution, we always need to show the degrees of freedom. And the degrees of freedom is always n minus 1. So it's always one less than the size of the sample. We've talked about t-distributions before, but just another quick reminder. Each t-distribution is specific based on its degrees of freedom. Um, and as you can see here, if purple is the normal distribution, degree 9 degrees of freedom is this blue, and a 2 degrees of freedom, so a sample size of 3, is this red. So as your degrees of freedom goes up, so as your sample size increases, this distribution, the t-distribution, begins to look more and more like the normal distribution. But when our sample size is small, you can see that our tails are fattier. We just have a little bit more probability in the tails. So they're similar in shapes to the standard normal curve. They're both symmetric about 0, single peak, and bell shaped. Like I was saying, the big difference is the tails. And so the t-distribution, especially in a smaller sample size, smaller degrees of freedom of that t-distribution, um, it will also have more probability in there. So how do we actually use a t-test and find the probability and all that jazz? So we're going to use our table B to find the p-val from the appropriate t-distribution. So in that example we were talking about before, we were trying to see, hey, these are our two hypotheses that the mean life of the battery is 30, and we're seeing if, hey, is it actually greater than 30? So that's our HA. When we do our t, finding our t score, you do x bar minus mu divided by sigma over square root of n and get a t score of 1.55 and the degrees of freedom of 14. Now, when I'm looking at this chart or the table, right, our degrees of freedom is on the left-hand side, so we're going to find 14, and the probability is in the top. So if we were trying to do like inverse t, we would go trying to find what t-score gives us a probability of blank in the tail. We would find our degrees of freedom and use the top column and find, okay, um, it's whatever's inside is the t-score. Since here our t-score is 1.55, you can see that not every t-score is going to be inside this table. So you just kind of have to find the range between them, and you see, hey, I'm in 14 degrees of freedom, and then between 1.345 and 1.761. So the probability associated with that, or the probability of getting t is greater than or equal to that 1.55, is somewhere between 0.1 and 0.05. So you see how like we could see that the t distribution or the t table isn't as great for finding the probability. It's not bad for finding the t star like we were doing in the confidence interval, but it's a little bit harder to go the other way. So we're probably going to want to use um, the inverse t or the t-CDF, and we'll see that here in a little bit. So I kind of talked about those first two bullet points. But the third one also, the reason why the table is not the best is because as we saw last chapter, the degrees of freedom only go 1 to 30, and then it skips every 10, 40, 50, 60, 80, 100, 1,000. So if your degrees of freedom, which is very likely not going to be on here, always round down. Always use the lowest degrees of freedom from the table. So if I'm at 45, I'm going to go down to 40 and get the most conservative estimate. Same caution right there. So let's look at this problem. Suppose we want to perform a test with H naught, our null hypothesis mu is equal to 5 versus our HA mu is equal to 5. At the significance level of 0.01, a random sample of size n equals 37 from the population of interest yields x bar is 4.81 and s sub x is 0.365. Assume the conditions for carrying out the test are met. Explain why the sample gives some evidence for an alternative hypothesis. Well, the alternative hypothesis is mu is not equal to 5. And since our sample is 4.81, Well, that's not equal to 5, so we do have some evidence to suggest this. The question is how significant is that evidence? And that's where a p-value comes in. So your sample either has evidence or it doesn't right away. And then you do a significance testing to see how strong is that evidence. So here I have some evidence to suggest PA, but we're going to see how strong it is. You could see, hey, n is equal to 37, so our large counts is good there because it's greater than 30. We have a random sample, so we're getting the random, and the size, or not the size, but 37 is less than 10%. Um, okay. We don't know the situation. I'm going to assume 10% or 37 is less than 10% of whatever we're finding. So we're good to go ahead and do this calculation. So we're going to do the calculations. If our n is 37, that means our t distribution is 36, or our degrees of freedom is 36, as you can see here. So we're going to do 4.81 minus 5 divided by our s sub x, 0.367 divided by square root of n, and get a t value of negative 3.17. So if we were to use the table, we're going to, even though our degrees of freedom is 36, we have to use 30 here, and we're trying to find 3.17 in the table. And it's between these two values. So the probability of getting a t value of negative 3.17 or more extreme is between 0.0025 and 0.001. All right. It's also good to know, as you see back here, right? The degrees or the probabilities are only of the positive values. So this is really getting a value of 3.17 and greater. So getting a 3.17 and greater. If I want to find the probability of it less than 3.17, well, since these are symmetric, the probability of getting 3.17 greater is the same as getting negative 3.17 and less than. So that's why in here, although it's all positive values, I can use it the same as negative this value and shading to the left. Okay. So T 3.17 is between 0.01 and 0.0025. And since we are doing a two-tailed test, since it could be either to the left, right, either shade to the left or shade to the right of the positive value, we have to double this probability. So we're really between 0.002 and 0.005. All right, and basically, essentially, since alpha is less than this, we're going to reject the null because we do have statistically significant evidence because our p-value is less than alpha, just as an FYI. But as you can see, that problem was kind of difficult because there's a lot of information that wasn't really in the chart, and it can kind of give us a rough estimate, not the best estimate. So we're going to suggest using technology to find your p-value. So let's do the same thing. I'm going to turn on my calculator. I'm going to go second distribution. And then normally we're doing normal CDF to find the value and inverse norm. Here we're now going to use TCDF. And I'm trying to find the probability of 3.17 and larger. So, or negative 3.17. So I'm going to do both of them to show you negative 1,000. This is the left-hand side, from negative infinity up until negative 3.17. And then comma the degrees of freedom, which is 36. And you can see, well, they doubled this, but so if I times this by 2, I get the same answer. So the probability of being from negative infinity up until negative 3.17 with a degrees of freedom of 36 is this value right here. We times it by 2 because our alternative hypothesis does not equal. So we're looking for either less than or greater than. So we have to double our p-val or our p-val. All right. So kind of putting this together to actually create not confidence, a hypothesis test. So state, we're going to do a four-step process: state, plan, do, conclude. State the hypothesis you want to test at the significance level, and define the parameter. So those three things: plan, identify the appropriate inference method or like the name of the test that you're doing, and then check the three conditions: the randomness, the 10%, and the normal slash large counts. And then in the do, um, if the conditions are met, you're good to proceed. Give the sample statistic, so that's our t-val, and I would probably use the formula. Or sorry, the sample statistic is our x bar, whatever your sample came. Your standardized test statistic is your t-val, and that would be your t-score, you could say, and that's t is equal to x bar minus mu naught divided by s sub x over square root of n, and then our p-value would be using that TCDF with the appropriate degrees of freedom. I would also add in here that I've written, write your degrees of freedom. It's good for you not to forget, and it's good for um, the grader to see that, hey, this is the degrees of freedom I'm using. And then make your condition, same way we did in chapter 9. If p-val is less than alpha, I'm going to reject H naught. If p-val is greater than alpha, I'm going to fail to reject. So why are the three conditions so important? We should be pretty familiar with it, but the three conditions allow us to actually use this formula here that has us finding the probability of getting an X bar, that value or that extreme. So number one, the randomness condition. The randomness allows us to say, hey, X bar is a pretty good estimator of mu, and therefore I'm going to use it in this test. Right? If this wasn't a random sample, if the sample was flawed some way, then I wouldn't use my X bar and I wouldn't want to use this formula because X bar isn't a good estimator of what the parameter might be. The second condition, the normal and large sample condition, um, this allows us to use the distribution of the standardized test statistic and use that t distribution, basically saying that this is relatively normal, follows that symmetric bell-shaped curve, and allows us to use a t distribution. And then the 10% condition allows us to use that formula for standard deviation for a sampling distribution, standard deviation of the sampling distribution of x bar. So basically, allows us to we're going to end up using s sub x because we don't know sigma, but we could use that s sub x over square root of n since the 10% condition is met. All right. And then here, this nice little picture is kind of the three possibility types for a one sample test. You're either doing your HA, your mu is greater than mu naught, so that would be a right hand tail, is less than would be a left side, and it does not equal is that two tail. It's looking at both sides. This one is where we do two times the probability of one tail because these are symmetric. Okay. And you find it, right? That t-val, whatever is the spot you shade, is based off of t is equal to x bar minus mu naught over s sub x square root n. Right. So let's look at a problem. The level of dissolved oxygen in a stream or river is an important indicator of the water's ability to support aquatic life. A research measures the dew level at 15 randomly chosen locations along a stream. Here are the results. An average dissolved oxygen level below 5 puts an aquatic life at risk. Do the data provide convincing evidence at the alpha 0.05 significance level that the aquatic life is the stream is at risk? So really, we're seeing is, hey, well, we would say, hey, our mu naught, our H naught is that, hey, mu is equal to 5. Our alternative is mu is less than 5. We're trying to see if actually does put people at risk or the aquatic life at risk, and that is when it is below 5. And then we're going to give a potential type 1 or type 2 error depending on our solution. So for state, we want to test, like I said, our H0 is mu is equal to 5, our HA mu is less than 5, where mu is equal to the true mean dissolved oxygen level in the stream using alpha 0.05. So your hypothesis, the parameter, and then the alpha level or the significance level. Those three things go in the state. In the plan, state the name, one sample t-test for mu, and then the three conditions. Random, the researchers measured the at 15 randomly chosen locations. Good there. They kind of get a little funny with it, but there are an infinite number of possible locations along the stream, so it isn't necessary to check the 10% condition. You could also just say that there are certainly more than 100, or there are more than, or 15 is less than 10% of all possible locations in the stream. Um, and then the plan. So our sample size is 15, which is less than 30, so that doesn't work. We don't know the population size, we don't know the population size, if that's normal, so that fails. So we do have to draw a graph. In this case, they chose to do a histogram, and they say it looks roughly symmetric and shows no outliers there. So our three conditions have been met. We are good to go on to the do phase. So I have my x bar, which is 4.771, my s sub x, which is my sample standard deviation. Again, you could do that. We could do this on a calculator. I'm not going to show you because it would take a while to type in. But if you were, turn it on. I'd go to stat, edit my list. So I'll just go into for, and by typing these in and so forth. And then when you go to stat, calc, one var stat, and then choose whatever it is. So this data is not going to match, but if you click on it, you're going to get your x bar right away and your sigma, your s sub x. I know it doesn't match because I didn't type this data in, but if you did, that's how you would get these values. So it's always good to state the values that you get, because let's say you typed in a number incorrectly, your x bar or your s sub x might be off slightly, but if you state it and state that that's what you're using, then the grader might give you more partial credit than, hey, this person just got a random t value that's not correct. I don't know what mistake they made. At least here they're like, oh, they probably just typed it in. Right? And the nice thing is x bar, we get asked this question right away. Does x bar give us some suggestion or some evidence? And it does, because we're looking to see if this is less, if the mean is less than 5. So the fact that our x bar is 4.771, which is less than 5, we do have some evidence. The big question is how strong is that evidence? When we use our formula, x bar minus mu divided by s sub x over square root of n, we get a t score of negative 0.94. So it's inside here. Our degrees of freedom is 15 minus 1, which is 14. You could use the table and see that it's going to be between 15 and 20. I'm kind of against that. We're going to go ahead and use technology. This is incorrect. That should be a negative, not a 2. So I'm going to go back a page. I'm just going to use it from on. I'm going to go second distribution. T CDF negative 1,000, comma, negative 0.94, comma, 14 are degrees of freedom. We get 0.18. So if we get it, that does fall in between the value on our table, which is good. And also it does match up. So our p-val is 0.1816. And so that's certainly larger than our alpha. So here's how we conclude. Because our p-val of 0.1816 is greater than alpha, which is equal to 0.05, we fail to reject H0. We don't have convincing evidence that the true mean DO level in the stream is less than 5 milligrams per liter. All right. And then the question 2 was, are we making a type 1 or a type 2 error? Now, since we failed to reject, we only have the possibility of making a type 2 error. All right, so we could make a type 2 error here. and they say ex- well, explain what this mistake would mean in context, or kind of give an example for what happened. So they say, if we did, then the true mean dissolved oxygen level mu in the stream is less than zero point 0.5 or less than 5 milligrams per liter, but we didn't find convincing evidence with our significance test. That would imply that aquatic life in the stream is at risk, but we weren't able to detect that fact. So this is kind of a really bad um, error to make, because on a type 1 error, the flip side would be, hey, we found that the true mean is less than zero point 0.5 when it's not. But if we found that it was less than zero point 0.5, we would probably try and come up with conditions and how to save the aquatic life. And so, yeah, we might spend money, but at least we wouldn't lose any aquatic life there because the mean is really higher than zero point 0.5. So, you had nothing to worry about. Here, it's actually less than zero point 0.5 potentially if we made this error, um, which could be very damaging because we would start losing aquatic life without even realizing it. This is a big, 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 big exam tip, except for all you lazy people who don't want to write things on your tests. If you're going to use the calculator work, okay, please, please write these things down. Okay, I'm just going to read this word for word because I think it's that important. If you give just the calculator results with no work and one or more value are wrong, either you typed it into your calculator wrong and that's why you got it incorrect, or you just wrote it down wrong, or whatever the case is, it's wrong. You probably won't get any credit for the do step. If you opt for the calculator only method, name the procedure like we do in the plan phase. Okay. Um, re- Report the standardized test statistic. I would do even more. I would say that the X bar, I would say S sub X. I would find our T val or T score using that formula. I would state the degrees of freedom, and then I would state the p val. Okay. Now you can find the p val. This is totally okay to find the p val like this. Um, but you should state all those other things in addition to it. Make sure you get full credit. Okay, this is a slight connection to chapter 10 a little bit, and some of you might have seen this connect in 9 to 8. Um, but the link between a two-sided test and confidence interval for a population mean allow us to make conclusions a direct conclusion from the confidence interval. Basically, they're going to match up really closely if you do a two-sided conf, significance test, which it's kind of intuitive, but um, if a 95% confidence interval from you does not capture the null value, we can reject H naught, that hey, mu is not equal to mu. And since we're just looking for, these are only for a two-sided. And remember, a two-sided significance test only happens when the alternative is mu does not equal whatever that value is. So you're looking for both sides. Um, So if the confidence interval doesn't capture it, that means the confidence interval is either completely above or completely below. Then we have evidence to reject H naught. Right. On the flip side, if the confidence interval captures the mu naught, then you should fail to reject, um, because we have some evidence to suggest that the mu naught is equal to whatever the interval is, so it's not far enough away. So there's a little bit of a connection between the two. Obviously, the same logic holds for any confidence level. So if this was a 99% confidence interval, then our alpha would have to be 0.01 and so forth. But this is kind of a good thing. And it raises the question, should we use confidence interval or significance testing? Well, right off the bat, confidence interval tells you more information than significance testing does. The significance tells you just based on a value, is this likely to happen or not? The confidence interval gives you plausible values for what our mu could be, right? So if we reject mu not saying, hey, it's not equal to that value, in a significance test, that's all it kind of tells us, hey, we have evidence that mu is not really equal to that. But in a confidence interval actually give you potential values, I think, that true mu is. So that's why a confidence interval is a little bit stronger of a statement. Let's look at another problem. At the Hawaiian Pineapple Company, the mean weight of the pineapples harvested from one large field was 31 ounces last year. A different irrigation system was installed in this field after the growing season. Managers wonder if the change will affect the mean weight of future pineapples growth in the field. To find out, they select and weigh a random sample of 50 pineapples from this year's crop. And A, B, C, D. We'll just kind of go through them as they come up. So, part A, state an appropriate pair of hypotheses for a significance test in this setting. Be sure to define the parameter. So, in the state, we have mu, or H naught mu is equal to 31, HA mu is not equal to 31. And then where mu, the true mean weight in ounces of all pineapples grown in this year. I would also add in our significance level. So I think it's going to come down later, but I would also state it up here so we don't forget, hey, alpha is 0.05. Because we need to state the significance level before we do a test. Before we do any information, any actual statistics, we need to decide what we're going to use. Part B, check conditions for performing a test in Part A. The three conditions: random, 10% normal, large sample. So random sample of 50 pineapples from this year's crop. Good there. 10% condition. It's safe to assume that 50 is less than 10% of all pineapples in a large field. And normal large sample n is equal to 50, which is greater than 30. So we've passed the central limit theorem. So we're good on that case. Part C says a 95% confidence interval for the mean weight of all pineapples grown in the years 31.255 to 32.616. Based on this interval, what conclusion would you make for the test of the hypothesis at the alpha level 0.05? So since 31 is not included in this, and that is our mu, our H naught, mu is equal to 31, we are actually going to reject H naught because 31 is not in that value. So we have some evidence to suggest against H naught and in favor of HA. So we have convincing evidence that the true mean weight of all pineapples grown this year is not 31 ounces because 31 is not inside that value. So we would actually reject the HO here. Part D is a good question. Can we conclude that the different irrigation system caused a change in the mean weight of pineapples produced? Explain your answer. Remember, this is a really good throwback to chapter 4. In order to prove a cause and effect relationship, you must do an experiment, right? If there's a difference between correlation and causation, a sample can give you some correlation. Hey, these two things seem to correlate. But in order to prove causation, that something caused something else, you must do an experiment. So here, this was not a randomized experiment. We just took a random sample of 50, so we cannot infer causation. It's possible that other things besides its irrigation system changed from last year's growing season. Um, so you can't prove causation. Only there's a correlation. Now, if we did an experiment and then did a significance test on that experiment, then you can start to get into that causal situation. This is kind of the last section for this video and for this chapter, but it's called using tests wisely. So they say statistical significance and practical importance. So statistical significance is not the same thing as practical importance. To help evaluate practical importance, give a confidence interval for the parameter in which you are interested. Confidence intervals are not used as often as they should be, where significance tests are sometimes overused. So sometimes you would just say, hey, a better reason why this isn't necessarily a good use or why statistical significance isn't always great. So say you took a sample and you got an X bar of, let's say, 30. Okay. Depending on what you thought your mu was, your actual mu, maybe you thought mu was 35, right? And you just kind of randomly pick whatever that mu is, and then you do a test, and you're like, I'm going to reject my. I have statistical evidence to suggest that my sample of this 30 was less than 35. So I've evidence. I reject H naught, and I have evidence in favor of HA. Now, since you're just comparing against some mu values, some H naught, it might not be a good H naught potentially. You don't really know. So that's why a confidence interval is actually a lot of times better because it won't just um, reject based on a specific value, but it could actually give me plausible values for that interval. So it won't just tell me, hey, is it less than 35 or not? It'll tell me a range of what they think this value actually is for that mu. So that's why confidence intervals are a lot of times a lot better, but they're underused quite a bit. And this is another a big beware sign of doing real statistics out in the real world. Um, so they say searching data for patterns is certainly legitimate. Performing every conceivable significance test on a data set with many variables until you obtain a statistically significant result is not. So essentially what they're talking about, this is called p-hacking. So basically what some people would do is they'd have their data set in front of them and they would just keep running test after test after test until they finally got one that was statistically significant. And then they wouldn't talk about the 10 other tests that they do, and they would just say, boom, here is one, it's statistically significant based on our data, and go from there. Now, one way against that p-hacking is, like I said, to state your alpha ahead of time before you do any testing, and make sure you're particular in what test you're doing. You shouldn't just be running every test left and right to, to try and find um, statistical significance. It should just happen or not based on the data you have and the conditions and all that. All right. So that is all we have for today in 11.1. So you should be able to state and check the random 10% and normal large sample conditions for performing a significance test. Calculate the standardized test statistic. That really is like our t-score that I was talking about. And it's t is equal to x bar minus mu naught divided by s sub x over square root of n. We will then take that t-score, go to second distribution, table down to TCDF to find our p-val, right? And remember, we use our lower bound, negative 1,000, comma, an upper bound, we'll keep it negative 0.94, and then our degrees of freedom right there, boom, and get our value out. That's our p-value. You'll be able to perform a significance test. We've basically just talked about the two main things. The only one we didn't talk about yet was stating the hypothesis. In the state phase, you state the hypothesis, the parameter, and the alpha value. And then once you get to here, after you get your p-val, you're going to conclude either reject or fail to reject. And remember, if our p-val is less than alpha, we reject H naught. If our p-val is greater than alpha, we fail to reject H naught. And then you can also use confidence intervals to help you make a conclusion for a two-sided test about a population parameter. Remember, this has to be a two-sided, okay? And that's all I have for you. So have a good rest of your time.